All right, so. All right, so one of the things I did say yesterday, like there wasn't much because we pretty much were doing the test most of the time, of course, some work time. So there wasn't much to be said, but the one thing I did say about homework was it was review from Algebra 2 stuff, factoring and canceling, getting common denominators. So that's what we're going to do in this section, this couple sections here with trig functions. We're going to apply algebraic techniques to the trig functions. Okay, so if you liked that in Algebra 2 and you know, manipulating x's and factoring, canceling, common errors, all that stuff, great, you're going to like it. However, if you weren't a big fan, then that's too bad. This will be, but it'll be a chance to get better at it, right, and get to see it over and over again. But it is something that we would use in calculus. There are many times that if, and again, I know I told you this at the beginning of the year, but if you, it's not the calculus that the students oftentimes will mess up on. It's the algebra that they have to do before they even get to the calculus, or maybe after the calculus have to do some algebra simplifying, and it's often the algebra. So understanding those things is important. Just like knowing the fundamental values of the trig functions on the unit circle come in handy, like right there. I just showed you that problem. It said arc tan of 1, and knowing that that's pi force, right, comes in handy in calculus, and it's a big advantage to know those and be good at those when you get to that, because you don't get hung up on that part of it. Right? You don't get hung up in the trig, you don't get hung up in the algebra, then you can focus on the calculus stuff. Okay? All right, so let's see, what do I got here? Number 40. Okay? So let's take a look at this. So it had some factoring and canceling stuff. All right, so right here, so you got x squared minus 9. Hopefully we all recognize that that would be x plus 3, x minus 3. The bottom has 4 terms. How do you factor something like that? It's called factoring by grouping. Okay, factoring by grouping. If you look at the first 2 and group those together, and you look at the last 2 and group those together, you'll notice that each one of those has a common factor. So right here we can factor out an x squared, and that gives us x plus 1 left. Right here we can take out a negative 9, and that also leaves us x plus 1. Now factoring by grouping only works, though, and these are going to be set up so that they do work nicely. Okay, factoring by grouping only works if when you factor out that common factor out of each one of those, that the thing you're left with is the same in both of them. So factoring out a 9, for example, here would not have been a good idea, because you'd have had negative x minus 1, and that's not the same as the x plus 1. That's why I took out a negative 9. Okay, and made that x plus 1. Well, now then you can take out, so now what you have is common factors here, right? You got these two, remember factors are things that are multiplied, so this is 2 factors, this is 2 factors. Well, they have a common factor of x plus 1. So you can take out an x plus 1, leaving you an x squared minus 9. Okay, so that's how this bottom one came to be. And then what can you do with this x squared minus 9? Factor that down into x plus 3, x minus 3. Now, as it turns out, we wouldn't have had to even done the x squared minus 9 and factor that, because we'd have had x squared minus 9 up here, we'd have had x squared minus 9 down here, and we could cancel those. Okay, but since I had already split those apart, split these apart, cancel those. Now remember, when everything cancels out of the top, you have to put a 1 there. Okay, and then you have 1 over x plus 1. So that thing reduces down. Now, why is that important in calculus? Because if we want to do some calculus to this, it would be very, very difficult. But doing the calculus to this would be much, much easier. So being able to reduce that down to that is a big advantage in the certain calculus situation. Okay? So we want to be able to do that. While we're talking about canceling, let's review some of the major pitfalls of canceling that you're not allowed to do. For example, if I have x plus 9 divided by 9, can I cancel those 9? No, you can only cancel common factors. Factors are things that are multiplied. 9 is not a factor of the top. 9 is not a factor of the top. Okay, so you cannot cancel those 9s. Now, a simple little test of this would show you can't. If I could cancel those 9s right there, the answer to this would be 9. Well, it's not. It's 18 over 9, which is 2. Right? It's not 9. So you can't cancel those 9s like that. It has to be a factor. Okay, so it has to be factored out. Now, what could I do with that? I could split it apart. Remember we talked about that earlier this year? I could split apart. As long as you don't split a denominator, you can split apart a fraction. You split the top up and put it all over that single denominator. So we could do x over 9 plus 9 over 9, which would be, I guess I would write that 1/9 x plus 1. I mean, we could do that. You could simplify that, but that's just kind of rearranging. Right? And that depends on the problem. I don't really call that simplifying, I call it rearranging. And rearranging is not always necessary, okay? It's kind of like what we do our 1 over root 3. To me, 1 over root 3 and changing that to root 3 over 3 is just rearranging. To me, that's not really simplifying. So one of the challenges we will have over the course of the next several days is to understand when it says simplify, how far do we go? What do we want our final answer to look like? And sometimes that's a little bit fuzzy, right? And we'll try to give you some I'll try to give you some guidelines on what we're looking for there. Okay, on the simplifying. All right. So here's 54. Okay, here's another one I picked, and if you got another one you want to do when we get done with this, we can do that. All right. But so here you got this big mess on the left. This is a times sign in between here. I started to write something else. That's a times sign in between. Now remember, when you have a fraction and you're timesing, is that even a word, timesing? I'm not sure that's even a word. It should be multiplying, right? So if we're multiplying two fractions together, you simply multiply straight across, right? Now, we could have reduced the 4 and the 6. I could have done that, which would have made the numbers a little smaller. That's fine. But I can always reduce here at the end also. Right? So whenever you're multiplying, you just multiply straight across. But if you want to say, okay, that would cancel into a 2 and this would cancel into a 3 or simplify up to down, whatever, you could do that too. And then you would get 9 over 14 right away. So maybe that's a better way. It doesn't matter. But at the end of the day, you multiply straight across. Okay? And you don't get common denominators when you're multiplying. Right? And when you're dividing, of course, what do you do with the second fraction? If this said divided by 6/7, it's flip it, and then it's multiplying. Okay? Now, when we're adding, that's a different story. When we're adding or subtracting, we have to get common denominators. Now, did Mrs. Andreessen talk about bow tie?
You mentioned it earlier.
The bow tie. I mentioned it. Oh, and we did it. We did something like it, didn't it? I showed you. Okay. Yeah, and that's what we can do on these two. Now, sometimes the thing about bow tie, that bow tie technique, I'll show you again, is it doesn't give you the least common denominator. Okay, and sometimes that might be what we want to do. So it might be better to just get common denominators, get the least common denominator. So we'll talk about that. Okay, so anyway, here we can factor because this is just a FOIL, even though it looks weird with the y's, but this would be an x and an x. That would make x squared, and then the 2y squared, that'd be 1y, and that'd be 2y. So it's just a FOIL with your last and your last and your first and your first, and then look at your outers and inners. You get 2xy and you get 1xy. 2xy and 1xy would add, those are like terms, and if you want a positive, you would put a plus with that and a negative with that. And that would give you 2xy and a negative xy, which would be positive 1xy when you put those together. Remember, when you combine like terms, you don't change them, right? When you add an xy with an xy, you don't get x squared, y squared, right? That's when you times them. When you add them, they stay the same. Just like when you add 3x and 4x, you get 7x. You don't get 7x squared, right? 3x plus 4x is 7x. So the powers don't change when you add like terms. So 2xy, negative xy, that'd be 1xy. Okay, so we do that to our top and bottom, so we get x plus 2y and x minus y. The x stays here. This you could factor out an x squared, which would give you x plus y. On the bottom here, that would be a FOIL as well. That'd be an x and an x. That'd be a 1y and a 2y. would give you 2y squared, and then sure enough, outers and inners, 1xy, 2xy would be 3xy. And that's why we don't write it yx, we always write it in order, so they look like common terms, because some people say 1xy and 2yx, those aren't like terms, but they are. All right. So now we can cancel, just like we were canceling the 2 with the 3. I can cancel the x plus 2y here and here. I can cancel this x with one of these x's, and so that would leave me 1x down here. And then nothing else cancels, and so it looks like I got an x minus y on top, and I got an x, and then 2x plus y is here, so that'd be x plus y squared. And that's it. That's as good as you can do, okay? So that's simple. All right, what else I got here? 62. Okay, 62 is, we're wanting to subtract two fractions. So now we need what? We need a common denominator. Now, it turns out we almost have a common denominator. We got x minus 5 and we got 5 minus x. Now, let's talk about that here real quick. Some people get confused when you take out a negative. Some people think that if you have a plus b and you take out a negative, it turns into a minus b. That's not true. That's not what happens, right? When you take out a negative, it doesn't change an add to a subtract. What does it do when you take out a negative? What's it do? It changes the sign of both of the terms. So it would turn this into negative a minus b, right? Now you can do a quick check, sure. So we would never take out a negative on something like that usually, right? Out of a plus b, but this is what it would do. And that would give you positive a and positive b. Where we usually do it is the reverse of that. If I had negative a minus b, then I would take out a negative, and then that turns into a plus b. But what did it do? It changed the sign of both of them. Okay? Well, here's where we usually want to take out a negative that's not quite so obvious. If I have x minus 5, and I take out a negative, it turns into negative x plus 5. Well, a lot of times we don't write that negative x plus 5. We flip it around to 5 minus x. So the lesson there is, by taking out, if you have a subtraction and you take out a negative, it actually flips the subtraction. Okay, it flips the subtraction. But the reason it flips the subtraction is you're changing the sign of both parts. Right? The x is positive here, the 5 is negative. If you take out a negative, it switches that. The x becomes negative and the 5 becomes positive. But it essentially flips a subtraction. So therefore, when I see an x minus 5 and a 5 minus x, I immediately think, oh, I'll just take out a negative and that'll flip that around. That'll flip that around. Okay? Now, if you want to go through 2 steps, take out the negative, make that negative 5 plus x, and then flip it, then that's fine. Okay? All right, so by doing that, then that's going to turn that negative. By doing that, if I take out a negative here on the bottom, I can take that negative and move it up here. One of the things I always talk to my Algebra 1B class about is when you have a fraction, you can write that as negative 3/4. You can write that as 3 over negative 4, or you can write it as 3/4 with a negative out in front. Whichever is the most appropriate for that problem, that's what you want to do. And where I show them that is if I had a problem like x, if I had negative x over 2 equals 7, we're doing some simple stuff in Algebra 1B. But if we're solving this equation right here, right, I tell them that I'd rather have that negative where? On the 2. I'd rather have that negative on the 2. They always say, I thought you were supposed to put the negative on the top. Well, you can. A lot of times we do want the negative on the top. If I write as a fraction, I usually do that. But in this problem, I'd rather have the negative down there. Because now I can multiply both sides by negative 2 in one step, and I'm good to go. So you can put the negative wherever you want in the fraction, just whatever makes the most sense. Well, on this one, if I've got a negative down here, I don't want it there anymore. When I take that out, I'm going to put it up here. Okay, now it turns out that once I put it up there, then that's going to turn into a positive. And now we got 2x plus 5 over a common denominator. Remember, when you add fractions then, you add the tops or subtract the tops, and then the bottom is the common denominator. Okay? Now, the advantage later on in calculus to doing that is, again, if we want to do calculus to this, a lot of times it's much easier to do calculus to a single fraction than it is to multiple fractions. So we want to get it written as a single fraction is sometimes to our advantage. Okay? All right, let's look at 64. Okay, so 64 is a little trickier to get a common denominator. This is where the bow tie could come in here. Okay, so let's review the bow tie. So the bow tie was when we wanted to add or subtract fractions, get a common denominator. We start down here and go up this way. So we take the 3x plus 4 times the 2. That would give us 6x plus 8. Then we start down here and go this way. 5x times that would be 5x squared, because we have to distribute, minus 15x. And then, all over the bottom, multiplied together. Now, that doesn't exactly look like a bow tie, but anyway, that's the idea. And you can't forget that last part. So the last part then would be x minus 3, and then 3x plus 4. We usually do not, here's the thing with bow tie. We usually want to go ahead and distribute or multiply these out that go diagonally. Because what we're hoping is we can combine some like terms. The bottom we usually want to leave factored, because what we're hoping then eventually happens is things cancel. Okay, so we're hoping some things will cancel, so we want to leave this factored. Okay, so what happens? Like you can see, I get that right there. We can combine some like terms. Now it turns out, if I did that right, I don't think anything cancels on that. I don't think this factors. We could try it, but it just, I tried. I couldn't get it to work. Okay, and certainly nothing down there that would cancel. So you just stop. All right, here's another question that often comes up. If you have 3x plus 9 over 2x minus 7, okay, let's just say we have this problem. What could you do on top? Take out a 3. Do you need to? What I usually say with simplifying, and this is just my rule, but why? Why take out a 3? It didn't really help you, right? To me, you factor something so that it serves a purpose. Like if you're solving an equation, set it equal to 0, you factor, each one of the factors could equal 0. Or you factor so that you can cancel with something. But if factoring out a 3 is not going to allow you to cancel anything, then don't even do it. Don't mess with it. It's perfectly fine to leave your answer like this. Now, I'm okay if you write it like that too. But my rule would be, if factoring out something doesn't then help you to cancel, then don't do it. Like if your final answer is 3x plus 6, just leave it 3x plus 6. You don't have to take out a 3, right? It does, because that doesn't lead you anywhere. Okay? Just leave it 3x plus 6. All right. And then the last one I have here, 66. Okay? So again, trying to get a common denominator. Well, if you have denominators that will factor, then you want to go ahead and factor those. Okay, so the left one factored into x minus 2, x plus 1, and then this factored into x plus 4, x minus 2. Now here's where bow tie would, I think, be a bad idea. Now it's not awful. It would be okay to do. Okay, I would still factor this first, probably like this. But of course, I guess when you bow tie, you would want it to be unfactored, because you'd want to take 2 times all that, and then you'd want to take 10 times all that, and that would be your top. Okay, but once you do this, if you have a fraction that's AB and another fraction that's BC, what's the common denominator? What? No, not the common factor. What's the common denominator? What's the common denominator between those two? ABC. Common denominator is ABC. Let me put it to you this way. What's the common denominator between 6 and 15? 30, right? Common denominator is 30. Now, the reason for that is this is 2 times 3, and this one's 3 times 5. Okay? So the common denominator is 30. What's this one missing? What will make this one be 30? What do you have to do to turn this into a 30? Multiply top and bottom by 5. That's because it already has a 2 and a 3, but it's missing this 5. So you would take this times 5 over 5. Now, what's this one need to turn into 30? you're going to times by 2. Why is that? Because it already has a 3 and a 5. It just needs a 2. See how the 3 is a common factor? We don't want to do 90. We don't want to do 2, 3, 3, and 5. That would be a common denominator, but not the least common denominator. So in other words, they both have a 3 already. So the common denominator is going to have 1, 3, but then it also needs a 2, and it also needs a 5. Well, this one's missing a 5, so we give it a 5, make it 30. This one's missing a 2, so we give it a 2, makes it 30, right? That's what you would do with numbers. So you do the same thing here with letters. This one already has an A and a B, but it's missing a C. This one already has a B and a C. It's missing the A. So you would take the top and bottom times A on that one, and you would take the top and bottom times C on this one, and that would give you your common denominator of ABC. Okay? All right, so what is the common denominator of this one going to be? They both have an x minus 2, but this one's missing a what? This one's missing an x plus 4. So it's got an x minus 2, an x plus 1, and now we're going to give it an x plus 4. So the top and bottom are going to get an x plus 4. All right, this one's got an x plus 4 and an x minus 2, but it's missing the x plus 1. So we're going to give this one an x plus 1 by multiplying the top and bottom by x plus 1. Okay? That's how you get a common denominator. Okay? It works whether you're doing 6 and 15 and turning them into 30. And it works if you're doing A, B, and B, C, and you're getting a common denominator of A, B, C. It's really the least common multiple is what it is. You take what they have in, you learned this in 8th grade, 7th grade probably. You take what they have in common, which is 1B, and you take the leftovers, the A and the C. You have A, B, C. Okay? So now, what do we get here? So we would get 2x plus 8, and we would get 10x plus 10, and you would add those together on top. The bottom, you'd have your 3x plus 4x minus 2x plus 1. Now, we see what we can do with that. We get 12x plus 9. Now, it would have been nice if something would have factored and we'd have been able to cancel something. That's what typically will happen. Well, nothing like that happened. Now, you might say, well, you take out a 3. And that goes back to what I was saying a minute ago. Sure, you can take out a 3, but that doesn't allow you to cancel anything. If there was a 4x plus 3 sitting down here, sure, that's what you'd want to do. Take out a 3, then your 4x plus 3 is be canceled. But it turns out there's not, so I say why do it? Just leave it like that. Okay? All right, what else? We're not doing that. Was there another question that came up there?
Number 41.
What did 41 say?
It's z to the third minus 8.
Z to the third?
Yeah, minus 8. Over z squared plus 2z plus 4.
Okay. Now, I don't know, Mrs. Andreessen still give you those factoring sheets with all the different factoring rules on it? And when you had it last fall, so you remember. Everybody else like, last year, I can't remember. And difference of cubes was one of them. Now, I always tell my calc students they don't have to memorize this, and so you're not going to have to memorize it in here either. But the pattern for a cubed minus b cubed was a minus b. Anybody remember? A squared plus AB plus B squared. The sign here is the same as the sign here, and then the sign in the middle changed opposite, and then it's no, it's starting to come back to it.
There's some word.
Was there a word for it? Oh, what is that phrase?
I don't remember. There's something like soap. Isn't it like soap? There's soap.
So,
Same.
Same, opposite, add, parentheses, add,
I know it was the same opposite add something.
same, opposite, add, but so is not a word, so she just threw a P on it. So, I don't know.
The thing too is positive.
Positive.
Same,
Oh, it's same, opposite, always positive.
same, opposite, always positive.
There we go.
There you go. So, same, opposite, always positive. Okay, there you go. Okay, and there's no coefficient on it. It's all ones. Okay, so that's the difference of cubes. Oh boy, that soap, that really helped you remember. All right, couldn't even remember what soap stood for. But you did remember. All right, so, all right. But anyway, that's what it would be. So the top would be z minus 2, because that's 2 cubed. So 2 would be like the b. And then it would be z squared plus 2z right? Because you got b is, in this problem, is 2, and the z is the a. So you got ab would be 2z. And then always positive would be plus 2 squared would be 4. So that's that one. And then this one factors into z plus 2 and z plus 2. You can see why I always put lines through my z's, because my 2's look just like z's. But z plus 2, z plus 2. And so you get nothing to cancel.
What's the bottom?
Did I?
Combine together, you get z squared plus 2z plus. Right?
No, you get 4z. That's the difference. Yeah, you get z squared plus 4z plus 4. Oh, wait.
Yeah. That's what I was thinking.
Wait a minute. No, time out. Well, okay, where did I go wrong?
That's where I was looking.
Yes, you're right. Well, I looked after you said it, I looked up, I said, oh, wait a minute. What did I do wrong on the bottom? That doesn't factor. That's not right. That's z squared. This would be z squared plus 4z plus 4, right? I just totally messed that up. And they did make it so it worked out nicely. Okay, so the bottom actually does not factor. The bottom doesn't factor. Okay, you can try to foil that and you don't get it, but it's a good thing because that cancels out from there. Okay, so the whole thing just reduces down to z minus 2. Okay, so final answer. Z minus 2. All right. So, all right. So now, what's this have to do with the trig stuff? Okay, so we're going to apply these very basic algebra things, same algebra thing. They should say basic, I guess. Makes it sound, that makes it sound simple, secondary, easy, right? Elementary, no, that's not any better. All right, so there's very complex, high-level algebra techniques that only the very brightest students can do. We're going to take those. We're going to take those and we're going to apply those to the trig functions, okay? There we go. That makes you feel better. All right, so in my constant effort to make life easier on you and harder on me.
Appreciate it.
You're welcome.
Trig cheat sheet, I like those.
So as I was spending hours writing out these notes, I thought, my God, this is going to take us the whole period for these guys to write these notes down. So
We should take the whole period to read them.
I did a little Google search for trig cheat sheet, and look what popped up. Now this is a lot of stuff, right? There's your unit circle on there. There's some good stuff on the front, but we want the second page, the back of the first page, okay? To the identity page. All right, now you might get, if you got a highlighter, you might want to get a highlighter or whatever. Pencil, you just have a pen or pencil. Okay?
Yeah, probably will share.
I have another one.
Trig cheat sheet. Well, no, I think I looked up trig identity. I started typing trig identity, and then one of the options said trig cheat sheet. I said, oh, boy, that sounds good. And it popped up. I actually looked at several, and then this one I thought, oh, this is good because it's got some other stuff in it too. So some of it's, a lot of other things will eventually, we've already learned, or things we will get to. And there's a few extra things that aren't in there. Okay, so first of all, and these are all listed in your book on page 372 as well. Okay, but the ones we're looking for here first would be the reciprocal identity. So if you look there on, I think there is a section that says reciprocal identities. So you just might highlight that section. Those should be things we already know, right? Cosine is the reciprocal of cosecant. Now make sure, I was talking to somebody at conferences the other day who was saying that they had for the longest time thought sine and secant went together. So you're right, it's sine and cosecant. But those are the 6 reciprocal identities. So you see those there. Okay, and then we've got the tangent and, we got the tangent and cotangent are actually sine, tangent is sine over cosine, so those are right above the reciprocal identities on here. So you got tangent is sine over cosine, and you got cotangent is cosine over sine, because they're reciprocal, so it makes sense. the nice thing about that, those two batches of identities, is it tells us that we can turn every trig function into sines and cosines. Because cosecant is 1 over sine, secant is 1 over cosine, tangent sine over cosine, and cotangent is cosine over sine. So we can always turn them into sines and cosines, which is going to be to our advantage sometimes. Okay, then we have below that on the cheat sheet, we have what are called the Pythagorean identities. Okay, the Pythagorean identities. So you can highlight those three down there. Now, the most important one here first is this one, the one that says sine squared plus cosine squared equals 1. Now, I think I may have talked about this one already, but if you go to the unit circle, right, and you look at this angle right here, and this is x, and this is y, and this is 1, it's pretty easy to see that in that triangle that x squared plus y squared is going to equal 1. That's why it's called Pythagorean identity. And in the unit circle, though, remember, x is equivalent to what? In the unit circle, x is cosine, and y is sine. So if x squared plus y squared equals 1, then cosine squared plus sine squared has to equal 1 also, right? And so sure enough, it does. Now take pi 6, for example. What's the cosine of pi 6? Square root of 3 over 2. Square that. What's the sine of pi 6? 1/2. Square that. What do you get? Square root of 3 over 2 squared would be 3/4. 1/2 squared would be 1/4. 3/4 plus 1/4 is 1. Sine squared plus cosine squared equals 1. Doesn't matter what order you do it. Now, keep in mind that when we talk about squared, and notice I left off the x. We often do that. We say sine squared plus cosine squared. We really mean sine of x squared or sine of theta squared and sine of cosine of theta squared. And this gets us into more trouble in calculus. So I'm going to be really picky about this. I know most trig teachers don't if they don't also teach calculus, because we often, matter of fact, what we do a lot of times is, and you guys will do this and I probably will too, is we'll get in a habit of sometimes just writing that. Now that mathematically actually makes no sense, but we will do it because we get tired of writing these parentheses all the time and so forth, okay? But what sine squared x really means, sine of x quantity squared, that's what it really means, but it gets to be a pain writing all those parentheses all the time. So we just have this shortcut notation, which is not going to hurt us at all right now. But sometimes when we want to solve equations or we want to plug numbers in, it gets to be a hassle and we forget about it, and it does cause us some grief in calculus sometimes. I've got to constantly remind them what this means. Okay, so anyway, sine squared plus cosine squared equals 1. Now we got these other two here. Well, these two just come from this one. So if I can use some more blue here, if I took this equation right here, so if you ever forget these, which you might, and on our next quiz, you're going to have to use these, and you will not get the trig cheat sheet on the quiz, I'm sorry to say. So, what if you can't remember quite what order these are? Well, you always can remember this one. You have to remember sine squared plus cosine squared equals 1. All you do is you take and you divide this one by sine squared on both sides. Now what happens? You get 1 plus, what's that going to be? Cotangent, gets cosine over sine, squared. This is going to be 1 plus cotangent squared equals cosecant squared. There's that one right there. Okay? Or instead of dividing by sine squared, multiply or divide both sides by cosine squared. What do you get? You get tangent squared plus 1 equals secant squared. And that's how you can remember. If you can't memorize them, all you have to do is take sine squared plus cosine squared equals 1 and divide by either sine squared or cosine squared, and it'll give you the other. Okay? All right. So, those are the reciprocal identities. Okay, now, you might want to jot these down off to the side there where you have a little bit of room. Since we know that sine squared plus cosine squared equals 1, it makes sense that we could subtract a sine squared from both sides, and that would also be equal. So cosine squared is equal to 1 minus sine squared. So in problems, when we see a 1 minus sine squared, we can replace that with cosine squared. And that can be to our advantage. So 1 minus sine squared is equal to cosine squared. And likewise, if we subtract a cosine squared from both sides, 1 minus cosine squared is going to be equal to sine squared. Okay? And then likewise, we can do that with these over here, right? Tangent squared would be secant squared minus 1. Cotangent squared would be cosecant squared minus 1. And then if you put some things together that we've already talked about today, remember earlier when I talked about pulling out a negative? It flips around to subtraction. So if you had in a problem, if you had sine squared minus 1, you might think after a few days of practice here, you'll go, ooh, geez, sine squared minus 1, that sounds a lot like 1 minus sine squared, and I know 1 minus sine squared is cosine squared. So if you see sine squared minus 1, you pull out a negative, now you got 1 minus sine squared, which is cosine squared. You know, so those are the kind of things, those are the kind of algebra things we're going to apply to this stuff. Okay? All right, next in line are what are called the cofunction identities. And those are, I think you got to go down a little ways to the bottom right-hand corner. The bottom right-hand corner are the cofunction formulas. Cofunction comes from the word complementary. Complementary means adds up to 90. You maybe remember from geometry, if you have an angle x, what's its complement? 90 minus x, right? If you have an angle x, say 30 degrees, its complement is 60. 90 minus 30. So if you notice in here, we have pi halves minus x. Well, that would be 90 minus x. So what we're saying is the sine of 90 minus x is equal to cosine of x. In other words, sine, and we already know this from the unit circle. The sine of 30 degrees is 1/2. That's also the cosine of 60 degrees, right? The sine of 30 degrees is 1/2. The cosine of 60 degrees is 1/2. So sine and cosine are called cofunctions. Oh, I wonder if that's how they got the name. Sine and cosine. Yes, that's where the Eddie's going to be the one like, if you tell me one more thing that I have to remember. Sine and cosine, that's where they got their name, the cofunction. Now, you're right, though, it does get into, wait a minute, okay, sine goes with cosecant when they're reciprocals, but now you're telling me sine goes with cosine when they're this. Yeah, that's true. It's a lot of stuff. I got it. Okay, that's why I got the cheat sheet. We'll get it. Okay, but, so anyway, that's how they got their names. Sine and cosine are cofunctions. Tangent and cotangent, right? Tangent of 30 degrees is 1 over root 3. Cotangent of 60 degrees is 1 over root 3. Okay? They're cofunctions, and so are secant and cosecant. But the word co comes from complementary. Complementary. The secant of 30 degrees is 2 over root 3. I shouldn't have picked that. 60. Let's do the secant of 60 degrees is 2, and so is the cosecant of 30 degrees. Okay? It's the reciprocal of sine, right? So anyway, those are called the cofunctions. We won't run into those that often, to be honest with you. Okay? All right. And then you've got the even odd. So those are back up right below the Pythagorean. And these are the last ones we're going to have. Okay? The even odd. Okay? If you remember, these over here are the odd. And these over here are the even. Okay? And what that meant is if you put opposites in, remember for odd, if you put opposites in, you get opposites out. So sine of negative x is the same as negative sine x. Sine of negative x is equal to negative sine x. Now what we're going to be doing is we're going to be doing the algebra stuff we talked about earlier, which is canceling, factoring, those kind of things. To cancel, they have to be common factors. So we're going to be doing a lot of substituting of things to make things simpler and to make things cancel. So all of the odd functions, sine and its partner, cosecant, tangent and its partner, cotangent. When we talk about partners, we're talking about the reciprocal partners now, right? Okay. Those are odd functions. So you put a negative in, it's like putting a negative on the outside. Putting a negative on the inside is like putting a negative on the outside. Even functions, opposites in, same out. So having a negative on the inside is like not having a negative at all. Okay? Cosine of negative pi halves is the same as cosine of pi halves. They're both even. Okay? So the even functions, you put in opposites, you get the same. So it's like the negative could just go away, is essentially what that tells us. All right. So those are the big ones. Those are the big identities. Some of that is stuff we've already learned. Some of it is, we can gather from the stuff that we've learned. Okay, so let's take a look. We're going to go over another thing when we come back. But let's just go through some examples. And when we come back, we'll just go through a variety of examples together where we see some different strategies along the way. Okay, all right. So everybody write down this problem right here. This is example 2 from your book, but it'd be better if you don't look at your book anyway. But if when you look in your notes, if you want to put these are examples of the book, you could always go back to the book to look at them if you need to. But there's going to be little tricks, I hate to call them tricks because it makes it sound like they're trying to fool you or something. Strategies. There'll be some strategies that you employ, and the more of these you practice, the better you'll get at seeing what strategy you should apply. Now, some of the strategies are like we did in the algebra, looking for factoring, canceling, those kind of things, looking for bow tie, getting common denominators. Those are things we want to be able to do. Okay? All right, so the directions on this one are simply to simplify. Okay? Now, if this was an algebra one, I would argue that there's really not much simplifying to do. Now, what do you mean an algebra one? Well, to me, this looks a lot like this problem right here. Okay? And what could we do to this problem right here? Factor out an x. And I just got done telling you that, unless you can simplify, unless you can cancel or do something, there's not much use of doing it. Okay? However, with sines and cosines, that changes a little bit. Okay? So let's go ahead and do it. So let's take out a sine x. Okay? Let's take out a sine of x. And what's that leave us with? It leaves us with, now you don't need the square brackets are the same as parentheses. Okay? We got so many parentheses with the sine x. Now, if you really want to be lazy, you could write this like this. Probably not going to take off points at this point. Okay, just leaving out the x now, which is weird because it's a function and that's a very important part of the function, right? But we can think of it as sine. So a lot of times you'll hear me, I'll just say, take out a sine, right? Now what I really mean is sine of x. Okay. Anyway, we get that. Now I just talked about this a minute ago. What should you think of when you see cosine squared minus 1? It's one of the things you wrote on your cheat sheet. If we would take out a negative, we could flip cosine squared minus 1 into what? 1 minus cosine squared. So I'm going to take out a negative, stick it out in front of the sign, and that now turns this into 1 minus cosine. Why? Because when you take out a negative, the cosine turns negative and the 1 turns positive. So the 1 turns positive, the cosine turns negative, so we can just flip those around. And what is 1 minus cosine squared? Sine squared. So now we have negative sine times sine squared, which is negative sine cubed. And that is simpler than this original. And so in algebra, taking out that x, getting y squared minus 1 doesn't really do much for us. It's just kind of rearranging things. But here, our rearranging actually benefited us because the 1 minus cosine squared can turn to the sine squared. Okay? That's the kind of stuff we're looking at doing. Okay? With our algebra. So, do one more real quick. 4 tangent squared theta plus tangent theta minus 3. And again, the theta is the x's. Those don't really matter here in what we're doing. So when we leave them off, that's not a big deal. So 4 tangent squared plus tangent minus 3. Does that make you think of anything? Well, you might have saw what I had up there before I covered. That's like 4x squared plus x minus 3. If you saw something like that, what would you think to do? Foil, right? So the directions actually on this one would be factor. You know, I told you factor, you wouldn't factor if you can't cancel, but unless the directions aren't a factor, if the directions aren't a factor, then that's what you want to do. So what do you do? Well, how do you make 4 tangent squared? Well, you either take 4 tangent times tangent, that would make 4 tangent squared, or it could be 2 tangent times 2 tangent, right? And so you try those, and you see your outers and inners, what those make, you know, to get your middle and all that stuff that you did before. So it turns out it's this. 4 tangent times tangents, 4 tangent squared. Outer would be 4 tangent, inner would be minus 3 tangent. So 4 tangent, take away 3 tangent is 1 tangent, and then negative 3 times 1 is negative 3. So it's just your FOIL factoring business, right? And that's it. Now, where that's going to come into play is maybe we have something on the bottom too, and then something could cancel. All right. Okay, let's try a few more here real quick just to give you some ideas and then maybe a little bit of time to work on these. But again, the idea is the algebra part of it. There's so many different things that you can do or try or whatever in a particular problem. And sometimes what's hard about these sometimes is seeing what to try. And so often you try something, you know, it's kind of like a fork in the road, you know, I'm not sure which way to go. So you go one way and it kind of hits a dead end. And so you come back and you try something else. And sometimes that happens on these problems for sure. And so what happens over time, the more practice you do on them, the better you are at picking the right road, you know, to start with. So that's kind of key. All right. So along this same line, just throw another one up here. I don't know if we need to do it necessarily, but just another factoring one. You know, when you remember the plus minus stuff, like if you have secant squared minus 1, that could be factored into that. Now that's if the directions are to factor. Okay, if the directions here are to factor, then that's what we could do. Okay, secant squared minus 1. Now, if we go though to the Pythagorean identities, right? What is another name for secant squared minus 1? Look on your sheet, the Pythagorean. Wouldn't secant squared minus 1 be tangent squared? Okay, so whenever you see a secant squared or a cosecant squared or a sine squared or a cosine squared, that's what makes you think of those Pythagorean identities. Okay, and remember, you can't just square something. This is another common mistake I see the accountant students doing. You know, you can't, like if you had x squared plus y squared, square root of x plus y squared is not x plus y. Okay, you cannot do that. That doesn't work, right? Because that'd be like doing square root of 9 plus 16, which of course we know is square root of 25, which is 5. But if you do the square root of 9 plus 16 and do 3 plus 4, that's 7. It doesn't work. It doesn't work to do the square root of that. So sometimes people think, okay, sine squared minus 1, I can do the square root of that and get sine minus 1. No, that doesn't work. Okay, so secant squared minus 1 could be written tangent squared. So if we may do some other problems where the goal is different. The goal might be turn this into sines and cosines. Turn this into a single term with sines and cosines. Well, in that case, you'd want to turn secant squared minus 1 into tangent squared, and then you'd want to turn that into sine squared over cosine squared. Now, the reason that works, remember, is, okay, tangent squared is really tangent quantity squared, which means that's the same as sine over cosine quantity squared. Now, that is okay to square the top and square the bottom when you have a fraction. Okay, these are all algebra rules, laws of exponents from Algebra 2 class. Okay, sine over cosine is tangent, and so tangent squared would be sine over cosine all squared, so you could do sine squared over cosine squared, would be tangent squared. So this could convert to this, right, if the goal was to turn it into sines and cosines. And sometimes that might be the goal rather than factoring. So it just depends on the problem. All right, So let's look at another one here. Okay, so let's say you have this one. All right, and again, the directions on this one might be to factor. Another problem we sometimes get into is they give you what they want you to turn it into. I mean, sometimes they actually will tell you what they want it to look like at the end. And then you have to do the steps to get it there. So sometimes that's good because, it's like the fork in the road. If you know where you want to end up, sometimes that's helpful in determining which way to go to get there. So that's sometimes helpful. Or sometimes we do a matching situation, like there'll be 3 or 4 different answers and you're supposed to get your answer to match one of those. And so you can at least have a little bit of an idea where you want to go, okay? But if the directions here said factor, we've got a problem because of what? Why couldn't we do a FOIL like on this right now? Because they're not the same. You got the cosecant squared and a cotangent in the middle. Okay, but when you see cosecant squared, go to your reciprocal, or excuse me, not reciprocal, your Pythagorean identities. What could we turn cosecant squared into? What would it be? 1 plus cotangent. So we can take the cosecant squared and we can replace it with a 1 plus cotangent squared. All right. Now again, I'm sure this sometimes seems like mindless exercises in algebra, and it might seem the same way here. But again, taking a longer view, and there are calculus situations for sure, but there are situations where by rearranging these, rewriting them, changing what they look like, it makes the next step in the problem much easier to do. And that's the goal. Okay, so anyway, if we rearrange now, we move this 1, since that's plus, doesn't matter, the parentheses don't really matter, so I move the 1 over there with the -3, which should be -2, and now we have a FOIL situation, right? So we got cotangent squared minus cotangent minus 2, so now we can factor that into cotangent plus 1 and cotangent minus 2. Okay. All right. Let's see what's next. Okay, here we got this one. Now, at first look, we've been doing a lot of factoring, right? We've been doing a lot of factoring here. But the direction on this one would be different. The directions on this one would be, let's turn this into sines or cosines or both. Turn this into a single term that involves sines or cosines. Okay? So we already got a sine, because there's nothing you can factor out, right? There's nothing squared, so we can't use our Pythagorean identities, right? So what we can do is change cotangent to what? Cosine over sine, okay? So we can take our cotangent, we can change that into cosine over sine. Okay, now remember, here's where those rules of multiplying fractions come into play. This is attached to this cosine, and we can put a 1 underneath this cosine now, okay? And we can multiply those together, right? You just multiply it. You don't need common denominators there. You multiply the tops, multiply the bottoms, okay? So this would be cosine squared over sine, okay? So cosine times cosine would be cosine squared over sine. Now I've got that sine over there. Now, if the only directions were change these into sines and cosines, you could argue that you could stop right here because that's all you have are sines and cosines. But usually it will mean a single term or a single fraction or something like that. Okay? So now we need to add these together. Well, now we need a common denominator. Okay? Now we need a common denominator. Now you got 1 and 2 ways to do it. You could bow tie, which would work fine. Or you could just say the common denominator is going to be what? Sine. This one needs a sine on the bottom, so you multiply the top and bottom by sine. Or if you bow tied, it would be sine times sine going this way. Sine times sine would be sine squared. Plus 1 times cosine squared would be cosine squared all over 1 times sine. It ends up being the same however you do it. Okay, but what's nice about that is you get sine squared over sine plus cosine squared over sine. Now you can add those together. You get sine squared plus cosine squared, but what is that? That's 1, right? So you get sine squared plus cosine squared. So again, get your common denominator here, so you'd have sine squared over sine, and then we can put those together, or bow tie, either way. Right, the bow tie would be here, sine times sine is sine squared, 1 times cosine squared is cosine squared, and then your bottom would be 1 times sine. Okay, and sine squared plus cosine squared is 1, so 1 over sine, which it says cosine. Actually, I think the directions on this one, if I remember now that I said that, the directions on this one actually were, yeah, they just said simplify. Okay, so the direction said simplify. So what does that mean? Well, a lot of times simplify. If you can't factor, if there's no factor cancel, the next strategy, get them in sines and cosines. Get them in sines and cosines, and then see what happens. Okay, and so yeah, you could just stop here. I think that's fine. To me, you stop there. That's okay. All right. So I would say either one of those. Pretty good. Okay, just a couple more here. This one would be a bow tie. Why don't you guys try this one? This would be a bow tie for sure, right? I mean, it's a common denominator one, but it'd be a really good one to do bow tie. Put the first step up there if you want to look, see how you did. If you got that far. Bow tie would be sine times sine squared. Then here, when you bow tie here, you've got to distribute, right? Just distribute as you do it. So cosine times 1, cosine times cosine squared. You got to distribute right there. And then the bottom is just that times that. Now what can you do from there? This and this make 1. Sine squared plus cosine squared would make 1. So you get 1 plus cosine over 1 plus cosine times sine, and then you can cancel those, because that's the factor of the top, 1 plus cosine. As long as you cancel the whole thing, right, you're good. And then that'd be 1 over sine, much like the last problem was 1 over sine. Cosecant. So, right, so a lot of times good things happen when we put these things together. All right. And when things work out, I mean, they're kind of fun when things work out, right? You know, not even when things are, you know, I mean, honestly, I don't want you to admit it in front of everybody, be embarrassing, but, you know, when you get a whole messy bunch of work on your paper, it works out, it's kind of fun.
Can't use that word again. I'd say nice, not fun.
Oh, you guys, killing me. All right, now, okay, write down this one. So Now this one, it doesn't seem like there's hardly anything you could do. I mean, this seems pretty simple. I mean, it doesn't have much in it. It's not. So this would be an example of wanting to get it into a certain form. So this is our last example. So this would be an example like, okay, we want to get this into, and I'd show you what you want it to look like. Okay, so you got it written down. Now let me show you at the end. Oops.
You know, I think I'd rather.
Let me show you the end right there. So write that down. Write that down off to the side. That's what we'd like to end up with. Okay. So this is almost like doing it backwards. You know, this could certainly be a problem as well. This could be a problem where I give you this and want you to end up there. Simplify. Okay. And so you would take this, probably turn it into sines and cosines, or maybe factor out a secant, maybe wouldn't be bad, whatever. There'd be some different things you could do with that. We'll get into it. Okay, but this is one where I show you where you want to end up and then what you're starting with and how we're going to do that. Okay, so that's another little strategy. Well, here what the strategy would be to be, okay, I got 1 plus sine x, but one of the things I know that I have that is nice is 1 minus sine squared. What's 1 minus sine squared? Cosine squared, right? Well, how can I get 1 minus sine squared? 1 minus sine squared is 1 plus sine and 1 minus sine multiplied together with FOIL, right? That's 1 minus sine squared or 1 minus cosine squared. So anytime I see a problem that's got a 1 plus sine or a 1 minus sine, I can think of that FOIL idea that can give me the 1 minus sine squared. So that's actually what we want to do here. We want to multiply the top and bottom times 1 minus sine x. Like that. Okay? So if we multiply the top and bottom times 1 minus sine x, now it gives us a messier top, so it gives us 1 minus sine x up there. But on the bottom, it gives us 1 minus sine squared, which is nice, because I noticed in my answer I had secant squared, right? I had a secant squared in there. Of course, that makes me think of cosine squared, 1 over cosine squared. So knowing where I want to get and seeing what was in there made me think, I'll bet there's got to be a cosine squared in there. And so if there's a cosine squared, it could come from 1 minus sine squared, and that's what would make you think to maybe try it. Okay? All right, so the bottom is just cosine squared. Right? Now, we talked about this earlier with fractions like this, where you have a single denominator. What can you do? Fractions like this, where you have a single denominator, what can you do? Split it apart, right? 3 plus 4 over 7 should be 1. That would be the same as 3 sevenths plus 4 sevenths. I could split that apart. I could put the 3 over 7 and I could put the 4 over 7, right? We can do, when we have a single denominator, we can do that. And that's what we have here. That's the advantage over the original problem. We can't split apart this. You can't do the reverse of that. You can't have 7 over 3 plus 4, which of course is still 1, is still 7 over 7. You can't do 7 over 3 plus 7 over 4. That doesn't work. That is not 1. So that's no good. But you have a single denominator, you can split it apart. So we're going to split that. Okay, now we just got to look at one piece at a time here. So I split this. I get 1 over cosine squared minus sine over cosine squared. So I split it apart. Okay. Now we look at each of those individually. Well, what's 1 over cosine squared? That's secant squared. So I'll jump ahead. That's good. That's what I wanted to end up with, right? But now, what about this? Sine over cosine squared. Well, now, it's a different kind of split. But I can make this sine over cosine times 1 over cosine. Remember, when you multiply fractions, remember what we said? You just multiply across. So I can take, so it's a different kind of splitting than what I did here. So I'm taking sine over cosine squared, and I'm making it sine over cosine times 1 over cosine. Okay, if you just look at this, hopefully you're convinced that that's the same as that right there. Right? Because what do you do with fractions? You just multiply them together. So that'd be sine times cosine squared, or sine over cosine squared. But the reason for doing that is what's sine over cosine? Sine over cosine is just tangent, right? So taking sine over cosine squared, I can make that sine over cosine times 1 over cosine, right? That kind of stays together as a thing. This is a separate term, right? The minus sign in between. So that's tangent, and that's secant. 1 over cosine is secant. So that's what we want to end up with. Okay? Fine. I know. You're right. I agree with you. All right. So, give time, no time. All right. So, you want to take pictures of the answer book? Fine. Calcchat.com. This might not be a bad time to use that if you haven't used it. There's a link on the website, but for our book, because these have multiple steps. I don't know when you look in the answer book. If you look in the back of your book, I'm not sure how much they work out for you. It's probably not really useful. Probably wasn't on today's either, the appendix ones, right? Because there's multiple steps, so you really need to see the worked out steps. So that might be a good time to use that. Okay? All right. So that's not very many problems. You probably 3 days, 3-day weekend, you probably have time for, 3 times the homework, really, right? Probably should have given you more, but
No, I appreciate it.
No, I think it's.
this is just fine. You can only stand to have so much fun on a 3-day weekend. Yeah, that's true. That's true. I mean, try to do as much as you can. Don't be afraid to go down the wrong road. I mean, too many times I think sometimes you look at the answers. You look at the answers to help you get started, but that's a problem. On the quiz, you're not going to have that. Getting started is the key, right? I mean, so don't be afraid to spend some time trying to get it before you cheat. Why, whenever anything's going on, I look up and Seth is right in the middle.
It's just
Oh wait, hey, I'm recording that too, so for all everybody.